The next part of the quantum theory that we need to study, it's still section 12.2 from your textbook, but now we're going to look at starting at page 624. And this is when we're going to look at photons and momentum. So last lecture we talked about photons being emitted. Now we also discussed the photon, we introduced it, and we said that a photon has no mass. And we know that momentum is equal to mass times velocity. Well, here's a little problem. If our momentum is mass times velocity, and we have an object with no mass, you'd assume it would have no momentum. But photon momentum is a little bit different, and we're going to get into that. We're also going to talk a little bit more about Peter Millikan and how he proved Einstein, because he wasn't actually seeking to prove Einstein. He was actually trying to disprove Einstein's theory. I'll get into that story here. It says by 1916, Robert Millikan, he established the charge of an electron as 1.6 times 10 to the negative 19. And with that ammunition in hand, Millikan set out to prove that Einstein's assumption regarding the quantum nature of light were incorrect. Millikan felt that there was overwhelming evidence for the wave nature of light. This is a picture here of Millikan standing next to Einstein. They were very, very famous physicists of their day. Of course, Millikan was the experimental physicist. Einstein was the theoretical physicist. And they disagreed over the nature of light. Einstein's theory basically proposed a wave-particle duality of light, which was not a very popular theory at the time. And Millikan, of course, was on the side of the wave theory of light, which had held for over 200 years by this point. So how Millikan ended up trying to disprove Einstein, he used a photoelectric device similar to the one that's shown here. Basically, it is a very sensitive galvanometer, so it measures very small amounts of current that pass through a circuit. So you see that it's connected through a potentiometer, or a resistor that can kind of change resistance. So this could set our voltage at different amounts, and it could measure currents in the range of microammeters. So what he did, he had this tube where electrons were being passed from the cathode to the anode, and he has shown light at it, and he was expecting to see that if it was possible to change the direction of the current by changing the frequency of the light. So that's basically what he's trying to do. And of course, so now it says here, when the cathode was exposed to light of various frequencies, the microammeter registered a current. The light had ejected electrons, which were attracted to the anode and then passed through the circuit. When the intensity of the light was increased, the current was increased. So to learn more about the kinetic energies of the ejected electrons, the polarity of the power supply was reversed so that the electric field between the electrodes would oppose the motion of the electrons. But Millikan discovered was that as he increased the potential difference, the current gradually decreased until finally it stopped flowing entirely. This opposing potential had turned back even the most energetic of electrons. So this is something that we call the stopping potential, which is the potential difference required to stop all photoelectrons from moving. So basically to cause a current of zero. Millikan ended up plotting this data for different metals, and what he ended up finding was that it predicted Einstein's theory exactly. So you could see what we have here is potassium, sodium, and zinc. The image that you would have copied from our last lecture, it's the exact same graph with three different metals, three different surfaces, and the y-intercept is the negative of the work function of each of those metals. The slope, of course, is Planck's constant as well. So much to Millikan's disappointment, he had proved that Einstein's equations perfectly predicted all of his results. He begrudgingly had to concede that Einstein's assumptions about the quantum nature of light were probably correct. So, in an attempt to disprove Einstein, he actually proved Einstein. So this is one of those examples of a negative results experiment, although it's still a useful experiment because his predictions were incorrect, but they did prove another scientist correct. Now, moving on from this, there's another effect that photons cause that could be studied as well. So, when Millikan's experimental results verified Einstein's interpretation of the photoelectric effect, the scientific community began to accept the particle nature of light. Physicists started to ask more questions about the extent to which particles of light, or photons, resembled particles of matter. And an American, Arthur Compton, ended up studying elastic collisions between photons and electrons. So what he did was he would have he would try to have photons and electrons collide, and he was trying to see if things like what we learned in Unit 2, the conservation of momentum, would apply with particles that have no mass, because he would assume they would have no momentum. So how is it that these particles that have no mass could have a momentum? And that was the big question. So now that it was kind of understood that people started to believe Einstein's wave-particle duality of light, this was studied a lot more. And in 1923, Arthur Compton discovered a phenomena that we now call the Compton effect, where he had high-energy X-ray photons. So he went higher up on the frequency of the photons, and he had them pass through a thin metal foil. And what would happen was he would have electrons emitted, but they would also have photons passing through as well. If you remember, X-rays can pass through quite a bit of metals as well. So these X-rays would pass through, but the photons would have less energy. And the loss of that energy would end up being provided to a photoelectron. So the electron would be ejected with kinetic energy, and the kinetic energy that electron gained was equal to the kinetic energy that the photon lost. And that's what we call the Compton effect. So he did this experiment with a number of different metals using different types of X-ray beams as well, and he found that the wave theory of light could not explain this well. Einstein's quantum theory of light did explain it well. So this was something that also strengthened the theory of the quantum nature of light as well. Going back to what we learned in Unit 2 about the conservation of energy and the conservation of momentum, through his calculations he found that both the conservation of energy and conservation of momentum were kept intact as well. And it says here that in this way, Einstein's ideas on relativity and the speed of light influenced work that confirmed Einstein's ideas about the behavior and characteristics of photons. So what Compton had to do in order to show that this was actually happening was he had to use, because these are high energy X-ray photons, they were moving at relativistic speeds. So he had to use Einstein's special theory of relativity equations in order to prove this. So as crazy as it is, Einstein ended up proposing theories about relativity that were later used to prove his theories about the wave-particle duality of light. So copy this down for the Compton effect. Then we'll do some sample questions on the Compton effect as well. The Compton effect is this elastic scattering of photons by high-energy photons. sorry, it should say the elastic scattering of electrons. Can you correct that, please? The elastic scattering of electrons by high energy photons. Energy and momentum are conserved. The momentum of a photon is equal to hf over c. It's also written as h over lambda. So let's look at a question here. So it says a certain AM radio station has a frequency of 1 megahertz. And then it also says that an FM station has a frequency of 110 megahertz. Radio waves are electromagnetic waves, so radio waves produce photons. Compare the momentum of the photons of the AM station with the momentum of the photons from the FM station. Well, what we'll do here is we have our momentum for the AM station is going to be equal to h over lambda or hf over c. In this case, it's going to be 6.63 times 10 to the negative 34. F is 1 megahertz, so I'll just put 10 to the power of 6 over c, which is 3 times 10 to the 8. I'll just do the 1 and let you end up doing the others. 6.63 times 10 to the power of negative 34 times 10 to the power of 6 divided by 3 divided by 10 to the power of 8. We end up with 2.2 times 10 to the negative 36. And if this is a photon measurement, so we would use the units of mass times velocity, so it's going to be kilogram meters per second. You can find the momentum of the FM station similarly, so I won't do that one. So now we have to compare the energy, and I'll find the energy just for the AM signal. The energy of the AM signal is h times f, and in this case, h is 6.63, of course, times 10 to the negative 34. Our frequency is 10 to the 6. So we just multiply those two, 6.63. Really, all we need to do is just find out what's the difference between 34 and 6. It's going to be, I'll have to write it as 6.6 times 10 to the negative 28 joules. Now it's two significant digits because I have a 1.0 megahertz, so there's only two significant digits there. Next question here says a photon possesses a momentum of 2.45 times 10 to the negative 32 kilogram meters per second. What is the frequency of the photon? And in this case, we know the momentum, so let's write down our momentum. It's rho equals h over, hf over c. If I need to find the frequency, this is momentum times speed of light divided by h. So momentum is 2.45 times 10 to the negative 32. C is 3 times 10 to the 8. And h is 6.63 times 10 to the negative 34. So it's going to be 2.45 times 3 divided by 6.63. And my order will be, let's see, I'll do this in my head. Minus 32 divided by negative 34 is going to be 2, and 2 times 10 to the 8 is going to be 10. So it's going to be F equals 1.11 times 10 to the 10 hertz. Now the next part says, where in the electromagnetic spectrum would this photon be? You can only really answer this using an electromagnetic, unless you know offhand where on the chart this would fall, and it's a radio wave. If you're given a question like that, you'll be given the electromagnetic spectrum in order to kind of help you answer that. You don't need to memorize those. So now we're going to get into the different types of photon interactions. So now that we know that a photon exists. We're going to talk about how do photons interact with the world. How does a photon interact with other matter? And there are 5 different types of interactions. You'll need to know all 5. So we talked about the photoelectric effect and the Compton effect, but these are the other ones as well. So the first one is one you're probably most familiar with. When you look at a mirror, you see a photon reflecting against the mirror. So the light that hits the mirror reflects almost perfectly, or in a perfectly elastic collision actually. It reflects off the mirror and it ends up going towards your eyes. So that is the first example of a photon interaction. It's reflection. And when you're asked to describe something like this, it is a perfectly elastic collision with a mirror. That's interaction number 1. The other one we know is the photoelectric effect. So this is when a photon interacts with an electron, and that's attached to a metal, for example, and the electron is ejected and becomes a photoelectron. So this is another photon interaction, is the photoelectric effect, when an electron is freed by a photon. So the photon gets absorbed by the electron, and its energy ends up moving to the electron and frees it. We also know the Compton effect. The Compton effect is when we have a photon, usually a very high energy photon, that has an elastic collision with an electron. The electron ends up gaining some of the energy of the photon, but the photon itself still also passes through and gets emitted, but it is then emitted at a lower energy level. So basically, the photon still travels at the speed of light, but with less energy and a lower frequency than it did when it first hit. So the Compton effect is our third one. We also have, so when we're talking about the photoelectric effect, one of the effects we had was when the photon was absorbed, and the photoelectric effect didn't happen. Well, what actually happens is the electron that gets absorbed, or that absorbs the photon energy, ends up entering into a more excited state. So if you remember from chemistry, when we were looking at what an atom looks like, electrons that are in a more excited state are farther away from the nucleus. So the electron that gets absorbed ends up moving farther away from the nucleus of the metal that it's attached to. So that's absorption. And then we also have this other effect, which is pair creation. So a photon can undergo pair creation, where it becomes converted into 2 particles with mass. So this process conserves energy and momentum because all of the energy of the photon becomes converted into kinetic energy of the new particles and their rest mass energies. So this one you'll look at more in university, but we do need to understand it here. Pair creation, basically, we have 2 particles created, and the 2 particles that are created are an electron and a positron. So a positron, we'll talk about that a little bit more in this unit, but it is basically something that looks like an electron, but it has a positive charge. So it has the same mass as an electron, but its charge is positive. So copy this slide down here. You may want to also copy a little bit of notes on what each of these effects are. These are the different photon interactions. They are reflection, the photoelectric effect, the Compton effect, absorption, and pair creation.